basically is in the shape of a cross that's canted with respect to the spacecraft in X direction by 26 degrees. So there are 5 separate channels, 5 separate receivers, which are coupled to the receiver telescope by 5 fiber optic cables. And so in a nominal 50-kilometer mapping orbit, the ground speed is about 1.6 kilometers per second. And that corresponds to a shot spacing of about 57 meters. And so this is the pulse tracking. The distance between the central pulse, number 1, and the outer spots is 25 meters. And each individual spot has a diameter of 5 meters. And each detector field of view around the spots is 20 meters. So this 5-spot footprint pattern is really important because it allows us to measure the slope in the cross-track and long-track directions. And as of March 2012, the mean ground track spacing at the equator was about 0.5 kilometers, and the maximum spacing between ground tracks was about 5 kilometers. Okay, so where can you get the LOLA data? There are 3 main sources. The first is the LOLA data node at internet.mit.edu. The second is the Orbital Data Explorer. And as we saw yesterday, it is basically a web interface for querying the LOLA data node, and it's really useful for selecting data by geographic location. And so these first 2 sources will give you the most recent data. We do also release our data every 3 months to the PBS, and you can get the latest PBS release at the Geosciences node website. So the LOLA data node website has 2 main links on it. The top one takes you to the actual altimetry data archive. The bottom one takes you to radio tracking and one-way laser ranging data. Most people are interested in the top one. So if you click on that one, that takes you to this web page. And I've included just a brief description of some of the different directories, but it's your basic PDS directory layout. So you have, for example, you have a browse directory which contains quick look images of data products, the RDRs and the GDRs, and these are useful for internet, for looking at your internet browser. And of course, there's lots of directories containing documentation on the instrument, data archive, data formats, and so on. And the data products themselves, of course, are the data directory, the EDRs, RDRs, GDRs, and SHDRs, and I'll talk about those in a minute. And we provide also some simple utilities for reading data within the software directory. And finally, the extras directory contains some unsupported but possibly interesting maps of geoid light illumination and global map of the Earth's exponent. So our lowest level data product is the experimental data record, EDR. And EDR is basically a time series collection of uncalibrated science and housekeeping data. And the EDRs are aggregated by orbit. So there's one EDR per orbit of about 7,000 seconds. And they start at each ascending equator crossing. And each EDR consists of 2 separate files. The first is the actual data stored in a PDS inclined binary table, and then you have your separate PDS ASCII label, which describes the table content. And so the label contains information like the start time, stop time of observation, product creation time, and so on. And it has pointers to descriptions of the various table fields. And actually, all of the data products in the archive are organized in that fashion. We have your data file and a separate label describing the data in the file. So the EDRs are useful if you want to do your own calibration and geolocation, which most people don't want to do. So basically, the EDRs contain no spatial information because the geolocation is done in subsequent processing. And that subsequent processing makes the reduced data records, RDRs. So the RDRs are time-ordered collections of calibrated geolocated measurement data, aggregated by orbit in the same way that the EDRs are. And each topographic return is located in respect to the lunar center of mass in a body that is rotating orbit frame, the so-called mean Earth polar frame. And the elevations are expressed relative to a reference sphere radius 1737.4 kilometers. So each RDR consists of a PDS table and a compliant binary table, and each table row represents a single 28 Hz LOLA minor frame with 5 spots. So the information for all 5 spots is in a single row. And the RDRs are useful for plotting and analyzing individual altimetry tracks at the full resolution of the instrument, whereas the gradient data products, which I'll describe next, are thinned and resampled and transformed. So the gradient data records, GDRs, are primarily raster digital elevation models formatted as IMG binary images with detached PDS labels. And owing to the large sizes of some of these files, we employ simple typing schemes. And we also use JPEG 2000 compression format, which is compatible with many software tools that everyone probably here is familiar with, ArcGIS and whatnot. And we also provide additional GDRs besides the topographic maps. We do maps of counts and slope and roughness. And like I said before, in the extras directory, there are maps of geolite, Earth exponent, and polar illumination. So most people are interested in looking at DEMs. And the DEMs come in 2 basic types, global and polar. And the global DEMs, like the one shown here, they are introducing cylindrical map projections, and they come in various resolutions from 4 to 1024 pixels per degree. So as of March of this year, the total global coverage for the 16 DPD map was about 90%. And so we interpolate the maps to fill in the pixels with no data. But if you're doing science on them, you may want to exclude those pixels, and that can be easily done using the counts maps that we provide. Just simply disregard pixels of 0 counts. Now, because of how it orbits, bunch up the poles and get wider apart from the equator, the largest gaps tend to occur near the equator. So we've been carrying out campaigns since summer of 2011 to fill in the largest gaps in our data with targeted off-meter slews. And these have been pretty successful. So far, the largest gaps between ground tracks is about 5 kilometers. This is something new. We're providing now maps of slope and roughness in the GDR directory. So this is the slope map, and it's at 16 dB. And this is derived basically by fitting a plane to 3 successive shots and requiring at least 5 valid ground returns within those 3 shots. So this is a bidirectional slope. And then the roughness is basically RMS roughness it's basically the RMS about plane fit, corrected for the number of degrees of freedom in that fit. Okay, so those are the global DEMs, and they also provide polar DEMs. And these are stereographic projected maps at resolutions of 5 to 400 meters per pixel. And so the polar DEMs come in various sizes. So the resolution determines the actual spatial extent of the DEM. The highest resolution ones are the smallest spatial extent. So in this example, the 5 meter pix map goes up to 87.5. And I think the 400 meter pix maps go up to 45 degrees latitude. And so just like for the global maps, we also provide counts maps for the polar PDMs. And again, these can be useful for, say, downloading certain pixels, they have low counts or no counts. And also, finally, I guess our highest level data product are the shade mirrors. And these are basically spherical harmonic expansions of lunar topography. And these are derived from the 1664 EDD maps. And they're just ASCII tables listing the degree, order, and the spherical harmonic coefficients. So these are useful if you want to compare topography with gravity and study crustal structure. Okay, so we provide several command line executable tools for outputting the RDR files. These are just simple Fortran programs, quick and dirty things, but they're very effective. And I guess the particular tool that you use will depend on the task at hand, what you're trying to do, how many files you're trying to work on, what information you want. So we have tools that will output ASCII comma delimited tables, or space delimited tables, or three-column binary tables. And I'll just briefly go over how you use the three of these to do data. So RDR to CSV, this writes the RDRs to lengthy comma separated value tables. These tables can be imported easily into spreadsheet programs. And to get a usage message for this tool or any tools, you just simply type it. You just simply type it with people with no command line arguments. And RDR to CSV requires that you have a each second kernel in the working directory, and we provide that kernel on the website. And so the CSV table is pretty standard output in engineering scientific units. But the table has 68 columns and it's over 700 characters long. So it's really best to just redirect the output to a file. And so here in blue, I just showed a simple example of how you can use it. You have to give it the name of the RDR, and at the end there, and an H, and the H tells us to include a one-line header at the top that describes the table columns. So each table row again corresponds to all 5 spots in a single shot. And you can find descriptions of the columns in the documentation on the website. So just to show you what the first 2 lines of that will look like in that case, you can see it's just a big mess of information that it's kind of hard to read. So a more useful tool is actually RDR to tab. This is more flexible because it gives lots of options. You can say, choose any particular combination of spots output, or you can exclude noise. You can tell it to express elevations relative to the GOA rather than the reference sphere. And you can also select data based on geographic location. So for example, suppose you want to output all spots and set the time origin to be at the beginning of the file, and want to include a one-line header at the top. Then you have to give it the name of the RDR you're working on, and then flags A, O, and H. And so the first 2 lines of output will look like that. And each row corresponds to a single detector, so it's broken up, the various detectors, and giving them each their own row. Now, if a particular detector doesn't record any returnables, then its entry is skipped, except for detector 1. If detector 1 doesn't record any returnables, then its foresight is geolocated onto the reference sphere so that you have a continuous ground track in the RDR file. So the first column is time, the second column, elevation, third column is the detector number. And I also want to point out that the third to last column is the flag value. Balance is 0 or valid ground returns according to a simple automated slope density test that's part of the pipeline processing. We found that it's best to use the end line option, which will tell it to output only points that have survived the subsequent manual editing that we do. So if you're running RDR to tab on many RDRs, it's really best to use RDR to XYZ to save time and disk space. So what we typically do is we'll use RDR to XYZ and we use that with flags A and M. A to output all spots and M to output only spots that pass the manual entity. And so this utility will output 5 separate binary tables, XYZ tables, one for each detector. And the XYZ values are launched to that to an elevation, but there are other options that you can use to tell it to output, say, return pulse width or return energy as a Z value. So I mentioned before that there are browse images of the RDRs, and this is one example. On the x-axis, it's seconds after start time in the orbit, and on the y-axis, it's the elevation relative to the reference sphere. So I want to show you this just to point out one thing to keep in mind when you're looking at the data and interpreting the data. And this signal anomaly, basically what happens is on the colder net side, the purple blanket encasing the instrument contracts and pulls the laser beam expander out of the long-range receiver telescope. And the end result is that on the net side, mainly detectors 3 and 4 get out of returns, whereas on the day side, all 5 detectors are working. So it's one thing to keep in mind. And another thing to remember is, as I said before, in December 2011, LRO moved to an elliptical orbit at Appalachian in the northern hemisphere of about 200 kilometers. And so this means that the range is actually too large to receive significant pulse returns in the northern hemisphere. So now, most of the RDRs from that time onwards will look like this, with sort of 1/2 kind of blank, nearly blank. Okay, so things you can do with data. Suppose you wanted to get all RDR data in a small geographic batch. As we saw in the talk yesterday, you can use the Lunar Orbital Data Explorer. And what you do is, on the main web page, you go to, you click on LOLA RDR Query. And that takes you to the web form where you can enter the longitude, latitude limits, or you can choose a specific feature. So for example, you choose crater trumpeter, and it will fill in automatically the long lat limits. And then you go down and click on query count, and it will tell you how many data points it found. And then you click on generate files, and you wait a few minutes. And if it works, then you get a listing of common set record value data files that you can download. So what you do then is create your own DEM from a crater. So say you want 100 pixels per degree. First you have to sort of massage the CSV files into the proper format for the software that you're using. And probably everyone here has their own preferred methods of making DEMs from sort of raw data. But so we like to use GMT. So I kind of wrote up this simple example. GMT to do that, and you don't have to worry about the actual details of the commands, but the basic steps are first you have to bin the data and compute the median within each bin, and then you interpolate over the map to create a group file, and calculate the gradient map for shading, and make a color table, and make a nice postscript image, and then overlap the bar. And if all goes well, you should end up with something like this. This should be on the road. So now I'll just kind of briefly go over some science highlights, show you other things that people are doing with the data. Jim Head and his collaborators have looked at global distribution of large lunar craters. They use the 64 PPD global DEM with crater tools extension to ArcGIS. And they cataloged 5,000 craters over 20 kilometers in diameter and analyzed the distribution and population characteristics. And this represented a twofold increase in the number of craters and size over previous work, which had suffered from heterogeneous illumination conditions and uneven coverage quality. So camera on Antarctica has looked at the polar illumination conditions, and he maps the permanent shadow regions using the 240 gigapixel LOLA DDMs. He's a big fan of MATLAB, so he used primarily MATLAB for this purpose. So here on the left is the map of the South Pole. In red are the 150 largest PSRs. And compared to previous studies, this work incorporated a more accurate and complete DEM with a higher flow ratio. And they increased computational precision and greatly extended the spatial and temporal coverage of the computer simulations that they used over the previous simulations. So Meg Rosenberg has looked at slope at multiple scales, and they created a global map of the Perspective line, shown here. And this can be downloaded from the data node. So basically the Perspective line is the slope of a deogram, and 3 example deograms are shown below, and it's on the deograms, it's basically plotting slope on the y-axis versus baseline. It's plotting slope at any baselines from 57 meters to about 2.7 kilometers. And they found that Mari tend to have complex deograms with low Pearson exponents, whereas the islands tend to have high Pearson exponent values. Basically, they're saying that Mari are smoother than islands. So Baker et al. Looked at geometric properties basins. They used 120 dpd local DEM with MATLAB and ArcGIS to develop a new semi-automated method of extracting topographic information. And this was especially useful because they did it in a systematic and reproducible way that accounts for complete azimuthal variations in these basins, which can be quite significant. So here's an example of this. So just summarizing, what's the bare minimum of what you need to know for the LOLA data? So what is it? It's a high-resolution, geodetically precise topography data set that includes the highest resolution grids and polar topography to date, and it's served as the current topographic records for the moon. There are 2 main sources of data online: Embryom.mit and the Lunar Orbital Data Explorer. The primary data products we provide are the EDRs, which are the raw data, RDRs, which are the calibrated geolocated data at full resolution, and graded data records, which are the maps, and the shaders, which are the spherical harmonic topography models. So there's lots of tools with data. Of course, you can plot, analyze, and individual tracks, RDR data. You can look at the DMs, the GDR data, and use various software routines like GMT, ArcGIS, and MATLAB. Of course, you can look at any kind of topographical characteristics like 1- or 2-dimensional slope and roughness, maybe catalogs of features like craters, study illumination conditions, crustal structure, and so on and so on. A few things to keep in mind for interpreting the data. Just remember that the geolocation is done in the inner polar frame, and the elevations are relative to the reference sphere. And so the genuine ground returns in the background processing are sorted from noise with an automated slope and density test and then subsequent manual editing. And the signal anomaly that's basically results in getting genuine ground returns from primarily the temperature stream 4 on the right side. And in December of last year, however, this elliptical orbit, so now most of the data remain in the southern hemisphere. Thanks.
Okay, thank you. This paper is open for discussion. Questions? I think we have Trent coming up here.
So I know you guys have a lot of different resolutions, and globally they seem to be still too sparse. What resolution do you think is? Thank you. What resolution do you think is good globally so far at the without having too much interpolation between the shots globally, I guess. So at the equator. Because
well, I guess it really depends on what you're trying to do, and the size of the features you're trying to look at. I guess my best advice would be to look at the maps and the counts maps and see how big the gaps are relative to the size of the features you're trying to look at. And if the features you're looking at are comparable to the gaps, then that is probably a sign that maybe you need to
shouldn't do it.
Think about it some more.
Okay. All right.
I don't know if that helps.
So one of your extras products is a geoid. How is that calculated? Is that calculated from LOLA data? Is that something you're getting from Grail or something else?
So I think that we provide right now 2 or 3 different geoid maps to kind of give you an idea of the sort of uncertainties. I think one of them is like an older JPL one. Another one is one that we have produced kind of in-house using historical data, and I can't remember what the one is. Currently, we don't have the Grail geoid. There has been some talk of incorporating that somehow into the processing, so that might be done in the future.
Okay, thank you.
Yeah.
Just a small sort of note. In one of your slides, you noted that a person would have to use the leap seconds kernel named NAIF0009. That one's going to be out of date in just a few days. And okay.
Yeah, well, we'll have to definitely get it updated in the next weeks.
I have a question, if nobody else has one. When you showed your tools, the RDR2, whatever, what platforms are they available for?
Oh, so yes, they're available for, I think, Mac, various Mac versions, Mac OS versions, and Linux, and I can't remember if they're available for Windows or not, but I think at least Linux and Macs.
And is it the source code or just executables?
Yeah, there's source code and executables and documentation. Yeah.
Okay, thanks. Another question?
Yeah, I was wondering about the laser reflectivity. How is that calibrated and what kind of units do you report it in?
Yeah, so that's a tough one. The reflectivity, I think there's still ongoing work on that. It was designed mainly as an altimetry instrument, so I think the reflectivity measurements are still lagging a little bit behind in terms of the calibration. I think right now the calibrations are from the pre-launch testing. Yeah, that's those things I know that.
All right, one more question.
Could that method also be applied with MOLA data for Mars? Is it the same as LOLA, or
Which method?
the reflective?
Yeah, so percentage of everything.
Someone can correct me, but I think there is reflectivity data from the molar experiment.
Yeah, we actually have a couple of papers on molar reflectivity, so I can give you some references if you like.
All right, thanks. Let's thank our speaker, and thanks for the discussion.